So next, I wanted to focus on gallium nitride pin devices, but the plan was to grow thicker gallium nitride pin diodes in the range of 3 microns to 13 microns, and that required an optimized fabrication process as well. I've talked about these points where I found the optimal growth conditions, I found the optimal eye layers, and I found the optimal fabrication conditions for the thicker devices. I still needed to tackle one issue, which is to take care of the high current flow along the mesa edge and to demonstrate a better design. So I've shown this that due to high current flow along the mesa edge, there would be premature breakdown of the devices. So I investigated simpler designs using Silvaco TCAD and applied them in MME growth. In this regard, I did a comparative study of two pin diodes, both with eye layer thicknesses of 10 microns. The difference between these two is that the right structure has a thin 50 nanometers of beryllium doped gallium nitride film sandwiched between the n-type layer, which would introduce a small barrier, resulting in more uniform current distribution across the device. As we can see that the current distribution improves from approximately 40% to 100% of the p-type contact of the device. And later I have shown in one of my devices that now the breakdown occurs across the bulk of the device and not along the mesa edge. Then I grew these gallium nitride pin diodes. This slide shows a layer structure diagram of my devices, where first I sandwiched a beryllium doped gallium nitride film inside the n-type layer, and the beryllium doping was 1 into 10 to the power of 17 per centimeter cube. And then I grew beryllium doped gallium nitride eye layers with eye layer thicknesses of 1, 2, 5, and 10 micrometers. And I kept the transition layer between the n-type and the eye layer to be graded junction for improved breakdown performance. Later, I deposited magnesium doped gallium nitride um, top layer with a cap layer as well. And once again, I kept the transition from the eye layer to the p-type layer is graded for improved breakdown performance. So I performed a study on cascaded nickel hard mask to create chlorine-based ICP dry-etched deep mesas for high-power devices. In this regard, I performed a study on 5 different kind of masks. The first one is positive photoresist, but I found its gallium nitride to mask selectivity to be very low, not suitable for our case. Then I studied E-beam evaporated nickel hard mask, but its yield was approximately 40%. Once again, not suitable for our study. Later, I performed a study on electroplated nickel hard mask. Its selectivity was high, but it is time inefficient, and also its chemical waste is expensive to dispose of. Later, I studied sputtered nickel hard mask. Its yield was 100%, and its selectivity was high, but it caused damage to the underlying gallium nitride films. So finally, I devised a novel procedure of nickel hard mask in which I first deposited a 50 nanometers of E-beam evaporated nickel, followed by 2 microns of sputtered nickel. It resulted in 100% yield, high gallium nitride to mask selectivity, undamaged underlying films, and I was able to successfully apply it to my thicker actual gallium nitride pen devices. And with this technique, we can also achieve thicker mesas. In this slide, I have shown the JV characteristics of my pin diodes for eye layer thicknesses of 1 micron, 2 micron, 5 microns, and 10 microns. And I've shown the maximum breakdown performances of each individual kind of devices as well. And the maximum breakdown voltage of 375 is a record breakdown voltage for gallium nitride based pin diodes grown via molecular beam epitaxy. Uh, One significant point that we see from comparison of the thicker devices versus the thinner devices is that the thicker devices show leakage current which is significantly lower, approximately 7 orders of magnitude lower as compared to the thinner devices. So we used a doping of 1 into 10 to the power of 17 per centimeter cube and achieved carrier concentration of 8 into 10 to the power of 16 per centimeter cube. And by comparison of our breakdown performance with the state-of-the-art quasi-vertical devices, we are comparable to the best MOCVD ground quasi-vertical devices, and we are the only group which are in the state-of-the-art MBE performance in terms of quasi-vertical devices. We achieved record breakdown performance and also record Baligas figure of merit for MBE ground quasi-vertical devices.